Good day, students. Welcome to part two of our calculations of areas using left endpoint, right endpoint, and midpoint rectangular approximations. So the instructions for example number two is as follows. We're to find the left rectangular approximation, the right rectangular approximation, and the midpoint rectangular approximation arithmetically, and then compute the area, the actual exact area with our calculator. And then we're going to represent our results graphically. Okay. So the function under consideration for number two is the reciprocal or the rational function f of x equals 1 over x. The interval is from 1 to 3, and we have n equals 4 equal subintervals. Okay, subintervals. All right, so let's go ahead and do this problem. So we're going to start with the left rectangular approximation, LrAM. Left rectangular approximation is equal to, we're going to be multiplying the width times. Now to determine what our heights are, we're going to set up an interval. Set up an interval to the right. We have 1, make this call for tick marks 1, so starting from 1, 2, and then 3. Okay, so say 1, 2, 3, 4, it's 2, 1, 2, 3, 4, that's 3. Okay, all right, so it's imperative that we create a number line so we can identify what our inputs are for the LRAM, RRAM, and MRAM, okay? So we're starting from 1 and going all the way to 3. Okay, the midpoint is going to be 1, 2, 3, 4, right there. So this is 1, 2, 3. Now we need to break it into 4 sub-intervals of equal width. So I'm going to subdivide this interval between 1 and 2 down the center. We know this is 3 over 2, or 1/2. And then the interval between these two, I'm going to divide it down the center. That's going to be 5 over 2. Okay? All right, now what does LRAM look like? For the left rectangular approximation, we're going to pick all the points to the left of the right endpoint, which is 3. Okay? So in this situation, let's label all our intervals that are our calibrations. So this is x1, this is x2, x3, x4, and x5. Okay? Now we're going to be picking x1, x2, x3, and x4 for our left rectangular approximation. All right, let's indicate that on our chart. So we're going to start from here and stop right here. See? This will be our left rectangular approximation LRAM. All right. Let's, while we're at it, why don't we just set up what MRAM and RRAM are going to be. For RRAM, the right rectangular approximation, we're going to pick all the points to the right of our left endpoint. So we're going to start from x2, x3, x4, and then end up in x5. All right, so it's going to look something like this. So from x2 all the way to x5, that will give us what our RAM is going to be. So this right here is our right rectangular approximation. For the MRAM, midpoint rectangular approximation, we're going to find the midpoint of all these calibrations we have here. So in between these two, that'll be our first point. 1, 2, 3, 4. Okay? So starting from 5 over 4 all the way to 11 over 4, that will be our MRAM. So let's indicate that graphically. We use a different color so you can see what it looks like. So we're going to go from here all the way to there. And this are the x values for our midpoint rectangular approximation. Okay, so this is for MRAM there. All right, now that we know what our inputs are for the function, let's go ahead and write down the formula for an LRAM. So for LRAM, we have the width of equal intervals times, let's see, f of x1 plus f of x2 plus f of x3 plus f of x4. Okay, now what is our width? The width is basically, we can see that we have uniform widths of 1/2, just to do it using the arithmetic or formulaic approach. To calculate the width, if you're equal, what we'll do is we'll calculate the length of the interval, which is 3 minus 1, divided by the number of intervals that we need, which is 4. Okay? 3 minus 1 is 2 over 4, which equals 1/2. So that's the width of our subintervals. All right, we're good to go. Let's go ahead and compute what LRAM is. That's going to be the width, which is 1/2, times f of x1, which is 1, plus f of x2. x2 is 3/2, plus f of x3. x3 is 2, plus f of x4. x4 is 5 over 2. Okay? All right, now all we're doing now is we're going to be evaluating the function for these respective input values. This function, all it does is it reciprocates, okay? So if we reciprocate the input, that gives us the output. Now, 1 over 1, reciprocate 1, you get 1, reciprocate 3/2, you get 2/3, reciprocate 2, you get 1/2, if you reciprocate 5/2, you get 2 over 5, okay? Okay, now if we plug in all this entire expression into a calculator, we'll get 77 over 60, which is approximately 1.2833. All right, so that's our left-hand rectangular approximation. Let's write it down here so you can see it clearly. So LRAM, left-hand rectangular approximation, is equal to 77 over 60, or in decimal form, 1.2833. All right, next we're going to move on to our right rectangular approximation, RRAM. Let's write down the formula first. Is the width times the function evaluated at all the points to the right of the left endpoint. So we'll have f of x2 plus f of x3 plus f of x4 plus f of x5. Okay, now we already calculated the width as being 1/2. We have equal subintervals of 1/2 in width, times f of x2, which is 3 over 2, plus f of 2, plus f of 5 over 2, and then the last one, f of x5, is f of 3. All right, and we already talked about what this function does, which is it just reciprocates the inputs. So we have 1/2 times 2/3 plus 1/2 plus 2/5 plus 1/3. Okay, now if you plug this into your calculator, you get 19 over 20, which is approximately 0.95. All right, so our right rectangular approximation is equal to 19 over 20 in fraction form, and it's approximately 0.95. Actually, that's exact. It's exactly 0.95 in decimal form. Okay, this is equal to 0.95. All right, our last approximation is the midpoint rectangular approximation. Let's go ahead and compute what that is. So for MRAM, we're going to be using the midpoint here. So MRAM is going to be the width times f of x1 plus x2 over 2. We're going to be averaging our calibrations, okay? So x1 plus x2 over 2 gives you that midpoint, and then x2 plus x3 over 2. That's how we are going to determine the input values for our midpoint rectangular approximation. Okay, so that plus f of x2 plus x3 over 2 plus f of x3 plus x4 over 2 plus lastly f of x4 plus x5 over 2. Okay, all right, so if you want to do the calculations, you want to average 1 and 3 halves. 1 is 2 over 2 plus 5 over plus 3 over 2 is 5 over 2. Half of that is 5/4. So if you do the calculations, we know that the width is 1/2. The first one is going to be f of 5 over 4. Okay, and then the next one, if we average 3 over 2 and 2 over 1, 2 over 1 is 4 over 2. So we add them together, you get 7 over 2. Half of that is 7 over 4. Okay, so there's basically a pattern. If you notice, you just have the odd numbers in the numerator, and then you have 4 in the denominator. Okay, so that pattern basically continues. For the next one, we have f of 9 over 4 for this average right here. And then for the last one, you have f of 11 over 4. All right. We know what this function does. It basically reciprocates, right? So we have 1/2 times 4/5 plus 4/7 plus 4/9 plus 4/11. Okay? Plug this in your calculator. You'll get 3,776 over 3,456, which is approximately 1.092 to 4 decimal places. All right, so our midpoint rectangular approximation is equal to 3,776 over 3,456, and that is approximately 1.0926 in decimal form. All right, so that goes our 3 approximations. Now let's compute the exact value of the area under the curve using our calculators. So the actual area is given by the definite integral from the lower endpoint to the upper endpoint of the function dx. Okay, so let's go ahead and use our calculator to do this calculation. I'm going to be making use of the TI-89 titanium, as you can see here. So let's go ahead and compute that. Let me use the area approach. You can do it here using F3, and to calculate the integral, we enter the function 1 divided by x, the variable of integration, x, lower bound 1, upper bound 3. Enter. That's the exact value. If you want an approximate numerical results, you hit diamond enter. Let's see, wait for a second. 1.0986. So that's the actual answer, okay? So that's approximately 1.0986 to 1 decimal place. Okay? So if you wanted the exact answer will be natural logarithm of 3, of course. Okay? Alright, so there goes the actual area. Now let's represent our results using a graph so that we can gain a deeper understanding of what our answers look like. All right, so I have four coordinate system set up here. Let's start with the left rectangular approximation, LrAM. Let's go ahead and graph the points. This is my y-axis, my x-axis. So we started from, let's see, this is 1, 2, 3. Okay, and this midpoint right here is 5 over 2, no, 3 over 2, and this is 5 over 2. Okay, perfect. All right, so let's grab the points. So for f of 1, we had it reciprocal. This is how I want to calibrate my y-axis. I'm going to use decimal points. Okay, so 1, 2, 3, 4, 5. This is 0.5, and then 6, 7, 8, 9, and that is 1. Okay, notice is our graph is going to be exaggerated in the y direction. All right, so f of 1 is just 1. So from here we have the first point of our rational function, and then 3 halves is 2/3, which is 0.66. So this one is going to go somewhere here. And 2 is 1/2, which is 0.5. 5 over 2 is 2.5. I mean, 5 over 2 is 0.4. 1, 2, 3, 4. And then 3, reciprocal of 3 is 0.3, 3, 3 repeating. So 1, 2, 3, this is 0.3. 3 is going to be somewhere here. All right, so that goes the points that define our the graph of our rational function. So let's go ahead and sketch the graph. So I'm going to connect the dots the best as I can. This is just a sketch, so oopsie, it's not going to be perfect. Or something like that. Alright, so what I did is I cloned my original graph 4 times, so I don't have to do the same thing over and over again. Alright, so let's do the LrAM. So for LrAM, we're just going to let the points to the left of our right endpoint determine the heights of our rectangles. Okay, so we're going to go from 1 to 5 over 2. So there goes the first point for the height of our rectangle, second point, height of the second rectangle, third point for the third, and fourth point for the fourth rectangle. Okay, let's go ahead and draw our rectangles that are approximating the area. So this will be the first height right here. This will be the second height, the third height, and then the fourth height. Okay, and then we just draw rectangles like that. So this is what the LrAM looks like. Something like this, and like that. Just connect it down like that. So, and connect it like that. And this one out, and then just connect it with this one right here. All right, so that's your left-hand rectangular approximation. All right, let me just make it look pretty. All right, next thing we're going to do is we're going to make a sketch of our right rectangular approximation, just to give you a visual as to what our results looks like. All right, so for the right rectangular approximation, the points to the right of the left endpoint will determine what our the heights of our rectangle. Okay, so we're gonna pick all the points to the right of the left endpoint. So we're gonna start from 3 halves. So this is 3 halves, and 2, 5 over 2, and 3. Okay. All right. So let's go ahead and draw our rectangles. So this will be for the first one, this will be the height right here, like that. And then for the second one, this will be the height. For the third one, this will be the height. For the fourth one, this will be the height. All right. And then we can go ahead and draw our rectangles to fit in, illustrating the right rectangle approximation. My lines are going a little bit off. Sorry about that. So there goes the first rectangle, there goes the second rectangle, there goes the third rectangle, and there goes the fourth rectangle. All right, and this one is your right rectangle approximation. Okay, how does the midpoint rectangle approximation look like graphically? Well, we're going to just be taking the midpoint of our calibration of the intervals to determine the height. Okay, so this midpoint right here, the center where it hits the curve, that's the first one. This is the second one, right in the middle. And then this is the third one. And this is the fourth one. Okay? Alright, so let's draw the top portion of our rectangles. So this is the first rectangle right there. This is the second rectangle, the third rectangle, and the fourth rectangle. Okay? Alright, let's draw rectangles illustrating the midpoint rectangle approximation. Right here. Like that. Like that. And that. Okay, so this is your MRAM. MRAM, the total area of these rectangles. So what does the actual area look like? Well, the actual area has no rectangles. Okay? The actual area is basically the area underneath the curve from 0 to, from 1 to 3. So this entire area right here, that is what the actual area is. Okay? Actual. Alright, so that's basically that. Thanks so much for taking the time to watch this presentation. You can feel free to subscribe to my channel by clicking here. And please post a comment to let me know what you think. I appreciate it. And do give me a thumbs up if you liked this clip. More clips can be found on mathgodserve.com/calculus. Thanks again for watching and have a wonderful day.